In Genshin Impact, it's a staple that 2:1 is the optimal value for your crit damage to crit rate ratio. But where does this number even come from? Spoilers, but crit damage being twice of crit rate isn't the full story. Hello, Count Sacke here, back with another Genshin Impact video. Today, I'll be showing how to mathematically prove that 2:1 truly is the optimal crit damage to crit rate ratio. To do this, I'll be introducing differential calculus, where I'll cover differentials, limits, derivatives, and lastly, optimization. This is part 1 in my series introducing calculus, and in the next one, I'll be talking about integrals. If you don't want to miss out on that, be sure to subscribe. And while you're at it, remember to like, share, comment, or leave a super thanks to help out the channel in the YouTube algorithm. I also have channel memberships where you can get access to exclusive videos, behind the scenes previews, and even no mid-roll ads during early access to videos. I would like to once again thank Eternal Dangowork for continuing to support the channel as a 5-star member. Lastly, I want to thank everyone who participated in the video topic poll, making this video possible. Alright, Lady Zibai is here, and she's eager to start the lesson, so class has officially begun. First, let's have a brief introduction to the topic. What is calculus? In a few words, calculus is the mathematics of change. It allows us to quantify changes, including relationships, on how one can affect the other. What makes calculus particularly special, though, is its ability to deal with continuously changing values. Take, for instance, it's easy to calculate the distance traveled for an object moving at constant speed, but what if that speed is constantly changing? Another case could be that you're given a graph of the distance traveled over time. What if you want to know how fast you were going at any moment in time? And actually, if you've ever seen any of my Genshin physics videos, you would know that I use calculus a lot, and that should show how fundamental it is. Given how important change is to calculus, it's important to ask, how do we quantify it? Consider this scenario. You're in Jueyun Karst, walking along the steep slopes, and with every step you take, you get more and more tired. Eventually, you manage to reach the top and find a place to sit and rest. As you listen to the breeze, you look down from where you came and can't help but ponder how far you've come. Though how do you exactly measure that? One simple way is to consider your current elevation and starting elevation at the base. If you subtract the two, you know how high you've climbed. While this number is easy to understand, you feel it doesn't quite capture your whole journey. Another option could be to consider how far you've traversed. By considering the change in your horizontal position, along with the elevation change, you can calculate the distance between your start and end position. This again is quite intuitive to grasp, but this once again fails to capture your hardship and effort. If you think about it, the reason why we're unable to get a more detailed look at things is because we're only considering two locations, the initial and final position. Instead of focusing only on the end goal, we need to think about every step along the way. For each step, you know that your elevation can change, but this also depends on where you are. In some places, one step forward could send you plunging off a cliff. In others, it could just be a small step up. Mathematically, we essentially want to find a function that outputs the change in elevation when you walk in a specific direction. Luckily, we have a quantity that does just that, the differential. We're about to get quite abstract here in a moment, but at the end of the day, I want you to remember that differentials can be used to calculate change. If you can understand that, then you understand differentials conceptually to a degree. Alright? You got it? Good. Let's proceed. Differentials are a specific type of one-form. A one-form is a linear function that takes a vector for an input and outputs a scalar. Because one-forms are linear, they have these properties. So if a one-form acts on a sum of vectors, you can apply the one-form to each individual vector, then sum them up. And then the second one is if a constant is multiplied to the input, you can factor out the constant and apply the one-form to the vector unscaled. To be more technical, differentials are a covector field that embodies the linear first-order change in a function at every point in any direction. To put things more simply, at any point on a function, the differential tells you how much change would occur in an arbitrary distance and direction. Consider this differential dx. If you input a vector with an x component of 2 and a y component of -1, dx of v will simply output 2. However, if you inputted the same vector into the differential dy, it'll output -1 instead. Notice from these two examples that the differential is essentially extracting the change on its respective direction. So dxv measures how much change happens along the x-axis and dy of v along the y-axis. Let's now consider a new differential, ds, which is equal to -4 dx plus 3 dy, and input the same vector v into it. What we find is that ds of v is equal to -11. This value shows that if you move 2 along the x direction and -1 along the y direction, the overall change in s will be about -11. If you want an analogy, consider the relationship between mass, linear density, and length. If you pick a point on a wire and then move a certain length, so essentially a change in length, and multiply that by the linear density, you essentially get the change in mass. In our case, the total change in a quantity is like the accumulated or removed mass. The vector is like the length but with direction, and the differential is similar to the linear density. In a way, a differential df represents the linear density of change in f. That is, it indicates how much potential for change in f is concentrated around a point. Once you input a vector into df, notated as df of v, that's when it measures the change across the length of the vector and along its direction. For our example with climbing Joy and Karst, the differential df holds information about the density or concentration of elevation change at points around the player's position. Once we input a vector that shows which direction and how far you'll walk, the differential will output the change in elevation along it. Now, say we have a function f of x. How do we calculate the differential of f, or what we call df? The first thing to note is that we want df to be a linear function, and since it's a function of x, we should expect it to be expressed in terms of dx. This means that df must be equal to r times dx. You should be able to see that this looks pretty similar to the equation of a straight line that passes through the origin, y is equal to m times x. In the equation, r is a scaling factor and can be interpreted as a factor that shows how strongly f changes when a change in x occurs. Though, how do we calculate it? Recall that df for a given change in x is a highly accurate approximation of the change in f, such that df of v is approximately equal to delta f, where delta f is equal to f of x plus delta x minus f of x, and that vector v has an x component of delta x. This results in delta f is approximately r times delta x. To make these exactly equal, we need to include an error term, which is itself a function of the change in x, epsilon of delta x. Now we can solve for r pretty easily. Here's the thing. Notice that we're technically considering finite changes in f and x. But remember from our hiking example, if we choose only 2 points, we fail to capture everything that occurs between them. This means we need delta x to be 0. However, if we substitute that into our equation, we have a problem. As can be seen, we get 0 divided by zeros, which are indeterminate. This might seem hopeless, as we somehow need delta x to be 0 so that we can fully embody all points on the function, but it can't since we get indeterminate. Lucky for us, there's a mathematical operator that actually solves this issue. It is called the limit. Imagine we have some sort of discontinuous function, f of x, that looks like this. At x equals a, there's a hole, meaning that f of a doesn't exist. Despite that, we can clearly see where the function is going. This is essentially what a limit is in concept. It determines what value a function approaches without ever reaching it. To reiterate, the core idea of a limit is that it approaches but never reaches. Let me elaborate on what we mean by approach. Consider a simple function f of x is equal to x squared. I want to calculate the limit of x squared as x approaches 2. But notice that we can approach from the left or the right. So which direction do we come from? Well, we actually need to do both. From the left, we can start from x is equal to 1.9, which results in 3.61. But why should we stop at 1.9? We could choose x to be 1.99, and this time we calculate 3.9601. But why stop there? We can get even closer to 2. Like x equals 1.999. This results in 3.996001. I think you can see the pattern now. In any case, let's now approach from the right. We can start with 2.1, which results in 4.41. But why stop there? We can do x is equal to 2.01, then 2.001, and so on and so forth, and we keep choosing numbers that just seem to get closer and closer to 2. Notice that throughout the calculation, we never compute x squared at exactly x is equal to 2. What we can observe is that it doesn't matter if we approach from the left or the right, the values tend towards 4. Because of this, we can say that the limit of x squared as x approaches 2 is equal to 4. Even though we can see that the limit would evaluate to 4, we never actually reach x is equal to 2, and never evaluate 2 raised to the second power directly. To understand this idea a bit better, Let's take a look at our first example with the whole. At f of a, it is undefined. However, the limit does exist. If we approach from the left and or the right, it looks like f of x approaches L. And because of this, the limit of f of x as x approaches a would be equal to L. I want to emphasize that in order for a limit to exist, both sides need to converge towards the same value. Consider this function g of x. At x is equal to b, it's actually defined to be something, but does the limit exist? If we approach from the left, we get one value. But if we approach from the right, we get a completely different one. Which one do we use? Because the function doesn't approach one specific value from both sides, we can say that the limit does not exist. To be specific, we say that the limit of f of x as x approaches a is equal to L if and only if the limit of f of x as x approaches a from the right and the left are both equal to L. One last idea before we move on. Limits can actually be used to define if a function is continuous. To get an idea for what continuity is in math, consider this example. Gaming needs to make a delivery from Liwa Harbor to Wangshu Inn. This isn't that difficult for him to do, as he simply takes the main road. Once he gets to Wangshu Inn, he finishes his delivery and heads back to the harbor with the same road. In this situation, the fact that Gaming is able to trace back his exact steps when going forward and back between the destinations tells us that the path he takes is continuous. He doesn't need to get off the road, climb, jump, or even fly. Here's another case, but this time to grasp the concept of a discontinuous function. Kirara needs to make a delivery from Inazuma City to Narukami Shrine. At first, the path is fine, but once we reach this part of the mountain, we have some problems. There are various segments where Kirara needs to do some climbing, and by the time she even reaches the top, it is very clear that there is no road that connects the two. When she goes back down, she doesn't always arrive at the same exact points when going up versus going down. Because the points we arrive at along the path change depending on which way Kirara goes, we can say that the path is not continuous. She needs to climb, she needs to glide, she needs to jump, whatever the case is. She can't just go by foot. All in all, we can say a function is continuous if f of a is also equal to the limit of f of x as x approaches a. Knowing this is actually very useful to us because originally we had to manually compute values over and over again from the left and the right just to see what a function approaches, which obviously gets very tedious very quickly. On top of that, limits also have other useful properties that allow us to algebraically manipulate them. This looks like a lot of stuff to remember, but it's not that hard. For the first one, it just says that if you have the limit of a constant, it doesn't depend on x, so naturally it doesn't matter what value x takes, it will always be equal to that constant. For the second one, we just have the limit applied to a constant multiplied to a function f. As we mentioned earlier, the constant doesn't depend on x, so we can actually factor it out of the limit and just apply the limit to f only. For the last four, you can basically think of it as different ways you distribute limits. Let's consider some examples so you can be more familiar with these. The limit of 3x squared minus 1 as x approaches 2. First, we can distribute the limit. And then on the second term, we can see that it's the limit of a constant number, so it just equals that number, which is 1. For the first term, we can factor out the 3 since it's also a constant, and then we can put the limit inside the square. From here, we can apply the limit and calculate the value to get 11. The limit of x squared minus 1 divided by x minus 1 as x approaches 1. Again, we start by distributing, then recognizing which ones are constants. In the denominator, we can apply the limit, and on the numerator, we can bring the limit inside the square, then apply the limit. However, we get something strange. The result is a 0 divided by 0, which is indeterminate. It looks like we don't get an answer, but let's check the graph of the function. Interestingly, we can see that it actually plots a straight line, but there's a hole at x equals 1. But remember, the limit doesn't actually care about what's at x is equal to 1. It just sees where things are going. If we look closely, the function appears to approach 2. There should be a way to get it somehow. To be specific, in cases where using algebra results in an indeterminate, it means that we need to do more work and simplify the expression first. Going back to the problem, notice that the numerator can actually be factored into x plus 1 and x minus 1. From here, we can distribute and recognize the constant and apply the limit, which gives us exactly what we expected, a value of 2. I just want to step aside here to emphasize that if you substitute x is equal to 1 into x squared minus 1 divided by x minus 1, it gives an indeterminate. However, when taking the limit as x approaches 1, we actually manage to calculate an exact value. So even if the result when directly substituting the value into the function does not exist or is indeterminate, the limit can still work out. Here's an interesting one. The limit of 1 divided by x as x approaches 0. While this looks undefined, let's see if manually calculating values will give us any idea. What we find is that if we take the limit as x approaches 0 from the left, we get negative infinity. However, if you take the limit approaching 0 from the right, you actually get positive infinity. As we can see, the one-sided limits don't converge to the same value, so therefore the limit does not exist. Now that we know how to calculate and algebraically manipulate limits, let's return back to determining the scaling factor r from earlier. Recall that we had delta f is equal to r times delta x plus epsilon of delta x, and solving for r results in r is equal to delta f divided by delta x minus epsilon of delta x divided by delta x. We can now take the limit as delta x approaches 0. However, we have a small problem. For the term with the epsilon, we should expect that as delta x goes to 0, both the numerator and denominator go to 0. So once again, this gives us an indeterminate, and epsilon of delta x may have an equation that cannot be simplified. So what do we do? Recall that r is defined in such a way that it accurately describes the change in f. This implies that the error must go to 0 a lot faster than delta x. If the error was comparable to the size of delta x, the function wouldn't be very accurate anymore. In short, delta x is small, but epsilon of delta x will always be even smaller. When you have a super extremely small number divided by a normally small number, the result will be approximately 0. This holds even more the closer delta x is to 0, so all of this is to say that the limit of epsilon of delta x divided by delta x as delta x approaches 0 is 0. Lastly, what we can do is substitute for delta f, which equals f of x plus delta x minus f of x. This results in the equation on screen. This quantity is what is known as the derivative. df dx is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. The derivative is the relationship that measures how a change in one variable affects the change in another. To put things simply, it is the rate of change in a function, but you can also think of it as being a type of sensitivity factor. The larger a derivative is, the more a change in that variable affects the change in f, and vice versa. With that understanding, its deep connection with differentials should feel natural. There are actually quite a lot of different notations for the derivative, but on screen are the most common ones. First is Leibniz notation, which looks like a fraction, but remember, derivatives are not fractions, they are operators acting on functions. So we often read it as df dx. Another notation is the prime notation, which simply is f prime of x. And the last one is this capital D with a subscript x. And by the way, one last common notation used specifically for a time derivative is this, f dot, which is equal to the derivative of f with respect to time. Personally, I have a special letter D that I always only reserve for differentials and derivatives as shown on screen. As you can see, I just put a little bit of a curl at the top. Just so you know, I will never ever use the prime derivative notation. I hate it with a passion. It's just something I really don't like. Anyway, to make sense of the notation, we commonly read it like this: the derivative of f with respect to x. The operation of taking a derivative is also referred to as differentiation. So if you took the derivative of f with respect to x, you differentiated f with respect to x. An important note about derivatives is that not all functions can be differentiated. In fact, two conditions must be met. First is that the function must be continuous, and the second is that it must be smooth. We already covered continuity under the limits chapter, but for a smooth function, this essentially just means that the limit of delta f over delta x must approach the same value regardless of if you approach from the left or the right. With all of that said, we finally have our equation for the differential. df is equal to the derivative of f with respect to x times dx. Let's have two examples. For the most part, this is just doing limits, so it should feel familiar. Here's a classic one. What is the derivative of x squared? To calculate it, we need to make use of the definition of the derivative. First, we expand the x plus delta x squared term. Second, notice that there's an x squared and a minus x squared in the numerator, so those can be cancelled out to 0. Third, we can divide the delta x. And lastly, we can take the limit, which results in 2x. If you wanted to get the differential of x squared, you'd simply have to plug things into the equation from earlier. so dx squared is equal to 2x dx. To conceptually understand this, df essentially contains information about how much x squared changes at any point along the parabola. In this case, we're specifically considering the change along the positive x direction. The derivative 2x is the scaling factor that shows how much a change in x affects the change in x squared. Notice that the derivative changes depending on what x value you start at. This should make sense. If we look at the increase in y from x equals 0 to 1, we'll see that y increases by 1. However, if we go from x equals 1 to 2, y increases by 3. For the second example, I'll do a hard one. Euler's number, in my opinion, is one of the most important numbers ever. In any case, it was first defined as shown. The thing about Euler's number is that its exponential has a very special derivative. So let's calculate the derivative of e to the x. First, we can make use of the multiplicative property of exponentials with the same base to split up the e raised to the x plus delta x. From here, we can factor out the e to the x from both the fraction and the limit. And now all we have to do is to figure out the limit. To do this, I'll let y equal the numerator, and from there I can express the denominator in terms of y. Also, since we're changing variables, we need to determine the new limit bounds. And we do this by essentially just taking the limit of y as delta x approaches 0. Alright, now we can rewrite everything in terms of y. From here we can notice that we can bring the numerator into the denominator by taking a reciprocal, and then I can make use of the power property of logarithms. Next, I'll make one last use of change of variables, where I'll let n equal 1 over y. Of course, with a new substitution, we need to calculate the new limit bounds. However, we already saw earlier that this limit does not exist, as it could either go to positive or negative infinity depending on the direction. Luckily for us, because this is merely a change of variables and not the main limit we're trying to evaluate, we can let n equal 1 over y if and only if the limit as n approaches infinity and the limit as n approaches negative infinity are the same. For the limit as n approaches positive infinity, this is literally just the definition of Euler's number, so that was easy. For the second one, we can make use of the fact that we can take the negative out from the bound and apply a negative to all n's in the expression. From here we just have to do a bunch of algebra involving exponent properties and fractions, but after going through it all, we end up with 1 plus 1 over n minus 1, all of that raised to the n. Now, this looks very similar to Euler's number, but it has this n minus 1. But the reality is, because we're dealing with infinity, that minus 1 really doesn't matter. Because infinity is so large, it just absorbs almost anything. Think about it this way. You have an incomprehensibly large number. Subtracting by 1 is barely going to make a dent. So in the end, you have the natural log of e and it equals 1 as well. So therefore, we know that the limit of e raised to the delta x minus 1 divided by delta x as delta x approaches 0 is also equal to 1. Therefore, the derivative of e to the x with respect to x is equal to e to the x. As you can see, obviously using the definition every time to calculate derivatives would be very annoying. Instead, what we do is recognize various properties and memorize a list of common derivatives. One of its most important properties is that it's linear. This means that when taking the derivative of a function multiplied with a constant, the constant can be factored out, and the second is that the derivative of the sum of two functions is equal to the sum of derivatives of the functions. And here are some basic rules to be familiar with, specifically the product rule, quotient rule, and chain rule. By the way, if you want to see the proof of these rules and properties, I have a members only video where I show how they can all be obtained from the original definition of the derivative. Lastly, here's a list of common derivatives. Let's try some examples. First is the derivative of the square root of x cubed. For this one, we can express the square root as raising it to the 1/2 power, then make use of the exponent properties so that we can multiply the 3 and the 1/2. And lastly, we can apply the power rule. In example 2, we have the derivative of x times ln x. All we gotta do is to make use of the product rule. On the first term, we can use the power rule to get the derivative of x. On the second, we have the derivative of a logarithm, and the rest is just doing some algebra. Alright, third example. The derivative of 3x squared plus 2e to the x divided by x plus 1 plus 5. We can start by distributing the derivative to each of the terms. The third term is a constant, so it cancels out to 0. On the first term, we can factor out the 3, then apply the power rule. For the second term, we have to make use of the quotient rule. Then recognize that we can use the power rule and the derivative of an exponential. After that, all we just have to do is simplification. On to example 4. The derivative of 5 times sine of pi theta squared with respect to theta. For this one, we can first factor out the 5, but then we have a composite function of a sine and polynomial. This immediately tells us that we need to use the chain rule. What I'll do is substitute pi theta squared with the variable u. So now we have the derivative of sine u with respect to u times the derivative of u with respect to x. The derivative of sine is cosine, and we can make use of the power rule and factor out the constants. With that, we have our final answer. Alright, last example. Let's put your chain rule skills to the test. The derivative of cosine of 2 sine of e raised to the 3x. For our variable substitutions, we can start from the innermost function, then work our way outwards. The innermost function is actually the 3x, so we'll let w equal 3x. However, we can still see that there are composite functions. Next, we have e raised to the w, so I'll let that be v. Then I'll let u be 2 sine of v. We've now managed to compact everything so that cosine is simply a single function with a single variable in it. And from here, I think you should be able to see why we call this the chain rule. One final thing to consider is that you can actually apply a derivative more than once. These are called higher order derivatives. For example, the second derivative of a function with respect to x can be notated as d squared f dx squared. For the nth derivative of a function, it has this notation. In my notation, it is as shown. Let's consider an interesting example. Calculate up to the fourth derivative of sine of x. For the first derivative, it's simply cosine of x. For the second derivative, we take whatever the first derivative was and differentiate it again. This results in negative sine of x. For the third, we differentiate again, factor out the negative, and then we have the derivative of sine again. Now for the fourth. Factor out the negative, differentiate cosine of x, and wait a minute, you get back to sine of x! You should be able to see that cosine and sine actually have a very interesting property where repeatedly differentiating eventually cycles back to itself. Interestingly, we also know that there is one other function that differentiating it results in itself, which is e to the x. I wonder if there's some sort of connection. I'm sure it's nothing important. We've talked about differentiating with respect to a single variable, but what happens if you have a function that has multiple variables? Those are pretty common, and well, the damage equation is also a multivariable function. So how do we calculate their differentials and derivatives? Say we have a function f of x, y, and z. For its differential, it would just be a linear sum of dx, dy, and dz with scaling factors multiplied to each. As we saw in the single variable function, we know that rx, ry, and rz must be derivatives. However, they're a slightly different type of derivative called a partial derivative. Common notations for the partial derivative can be seen on screen, where we have this curly d symbol. This means that df can be written out as such. df is equal to partial x of f dx plus partial y of f dy and partial z of f dz. Luckily, partial derivatives share the same properties as the ordinary derivative. The only thing to keep in mind is that a partial derivative will only consider the change of one variable, which is the one it is taken with respect to. This means that all other variables are treated as constant. Let's have an example. Calculate df if f of x, y is equal to e to the x tan of y plus x squared minus natural log of y. Since this function has two variables, x and y, we need to take the partial derivatives with respect to both of them. When partially differentiating with respect to x, we can distribute the derivative. For the second term, we differentiate ordinarily. For the other two, remember that the variables that aren't x are assumed to be constant. This means that tan of y and ln of y are basically like constant values. So on the first term, we can factor out tan of y, and on the third, it's equal to 0. For some student participation, you guys try calculating partial y of f and df on your own. Feel free to leave your solution in the comments. And by the way, this is the final answer for those who want to check their work. Earlier I mentioned that derivatives can measure the rate of change in a function with respect to a change in a variable. In this interpretation, it means that when the derivative has a positive value, the function will be increasing along that direction, but if the derivative is negative, it will be decreasing. But there's also the case where the derivative is 0. This implies that the function wouldn't be increasing or decreasing, so it must be constant. Let's say we are approaching a hilltop. In this scenario, the direction the player is moving refers to the positive x direction, and the elevation of the hill is the function. When approaching the top, we can see that as the player is moving forward, their elevation is slowly increasing. This would correspond to a positive derivative. At the moment the player reaches the top, the elevation barely changes. This means that the derivative is roughly 0. And if the player continues to move forward, they start to slowly go down, so the derivative would have to be negative. The important part to know is that when the derivative of a function is equal to 0, it means that the function isn't increasing or decreasing with respect to a change in that variable, and is therefore either a minimum or a maximum. Now, a function can actually have multiple locations where its derivative is 0, meaning that there can be multiple minimums and maximums. In the case of multivariable functions, you find where all partial derivatives are equal to 0, and that would be where a minimum or maximum would be located. A good question to ask is this: how do we know if a point is a maximum or minimum without plotting it? Well, there are many ways to do this, but I'll just cover one of them, which makes use of the sign of the derivative. Before a maximum point, the function should be increasing, meaning that if we choose a point slightly less than the maximum, the derivative should be positive. After a maximum, the function should be decreasing, so at a point slightly larger than the maximum, the derivative should be negative. In the case of a minimum, the function should be decreasing before it and increasing after it. Therefore, the derivative must be negative and positive respectively. Here's a table for your reference. Let's try an example. Find the maximums or minimums of the function x cubed minus 2x squared plus x plus 1. So first, we need to calculate the first derivative. You can distribute the derivative, then we have a derivative of a constant, so that cancels out to 0, and the rest we can just use the power rule. Next, we set this equal to 0 and solve for x. In this case, we need to make use of the quadratic formula. In the end, we get x is equal to 1/3 and 1. Now, let's check which one is a maximum and which is a minimum. I'll consider a point 0.01 to the left and right of each. At x equals 1/3, we can see that the derivative is positive on the left and negative on the right. We therefore can say that x equals 1/3 must be a maximum. For x equals 1, the left is negative and the right is positive, so it must be a minimum. And sure enough, if we check the graph, we are correct. In theory, if we took Genshin's damage formula and took its derivative with respect to a specific stat, we could find the value that stat needs to maximize damage. However, in reality, it's actually much more disappointing. In most cases, you'll just find that it has no finite maximum. The problem is that with the damage formula alone, we have no limiting conditions on our stats. This means that our stats could just keep growing and growing to infinity, which obviously doesn't happen in-game. To be general, we need a way to optimize a function under specific conditions. One possible way to do this is called the method of Lagrange multipliers. And here is the equation for it. The triangle with an arrow over it, also called nabla, is the del operator, which is just the partial derivative with respect to each variable. f is the function we want to maximize, lambda I is the ith Lagrange multiplier, which are constants, and gi represents the ith condition. As can be seen, we're not just taking the derivative and setting it equal to 0. There's also this additional term with lambda I and gi. Here's an example. Let's say we want to find the maximum or minimum of the function f of x and y, which is equal to x times y, with the constraint that it is along x plus 4y equals 16. First, let's determine g. Basically, all we have to do is to put everything on one side. Next, we can use the main equation and substitute. Because we have two variables, nabla contains the partial derivatives with respect to x and y, resulting in two different equations. I'll start with the x partial derivative. Try to follow along and identify what I'm doing throughout each step. For example, am I distributing? Am I factoring out things? Am I making use of derivative properties and whatnot? Now for the partial derivative with respect to y. With that, we are left with 3 equations and 3 unknowns. And because the number of equations equals the number of unknowns, we can actually solve for everything. It just takes a little bit of algebra. We find that x and y are equal to 8 and 2 respectively. If we substitute these back into the original function, we can find the maximum or minimum with our constraint. F of 8, 2 is equal to 16. Alright, armed with differential calculus, we can now optimize our average damage based on crit rate and crit damage. Here's the damage equation as you might know. In our case, we're only focusing on crit rate and crit damage, so we can essentially ignore almost everything in here. I'll also be simplifying the equation with just letters rather than text. In short, this basically says that our damage is proportional to crit, which should make sense. Also, let's consider the average damage and average crit, so D is equal to alpha times C average, where C average is equal to 1 plus crit rate times crit damage. Crit can come from many different sources: artifacts, weapons, food, leveling up, character buffs, elemental reaction buffs, selectable buffs, among many others. We could spend time writing out the equation for each of these, and that would take forever, but there's something we can do to greatly simplify things. The total overall crit rate and crit damage is simply the sum of the respective quantities over all sources. Another observation we can make is that crit damage is always twice that of crit rate. Essentially, we can state that for any crit damage and crit rate, there's a common value that the two have a direct relationship with. For crit rate, it's equal to that common value, but crit damage will be twice of it. In addition, further upgrades can be accounted for by considering a multiplication factor. Mathematically, we state this: CRI is equal to NRI CVI, and CDI is equal to 2NDI CVI. CRI and CDI are crit rate and crit damage from the ith source. NRI and NDI are the multiplication factors that accounts for upgrades in the source, and CVI is the common crit value for the ith source. Quantities with a subscript of R relate to crit rate, and the subscript D is for crit damage. To understand the multiplication factors, think of artifacts. When you level up an artifact, its major affix increases by a specific set amount. Each upgrade can essentially be considered as a certain percentage increase in the stat. The multiplication factor n is essentially just that, the percentage increase of an upgrade from the crit value. This doesn't just apply to the major affix, by the way, it applies to the minor affix too, and any other source of crit. Consider this example. Say your crit rate minor affix upgrades were 2.72 and 3.89, while your crit damage upgrade was 7.77. I'll define CV to be equal to 3.89, but you're actually free to use a different value. The important thing is that CV is just a constant. What we would calculate is that NR would be 1.7 and ND would be equal to 1. There's one last consideration that we need to make, and this is very important. The amount of upgrades that we can do is limited. This means that our multiplication factors are also limited. To embody this condition, I'll introduce a new variable, capital N, which is equal to the sum of the crit rate and crit damage multiplication factors for the ith source. NI can be understood conceptually as a quantity that represents the current maximum percentage increase that can be allocated to crit rate and crit damage. In our example from earlier, we computed that NR was equal to 1.7 and ND was equal to 1. This implies that capital N will be equal to 2.7. You have 2.7 upgrades available, where each upgrade is worth 3.89%. 1.7 upgrades of 3.89 go into crit rate, which results in 6.61, and 1 upgrade of 3.89 times 2 goes to crit damage, which is just 7.7. With these formulas in place, we can now proceed with optimizing damage. As discussed earlier, if you have an optimization problem under specific constraints, you can use the method of Lagrange multipliers. In our case, we want to maximize the damage, so F is equal to D. For the constraints, it is that the sum of the scaling factors must equal a constant for each source, which is the NRI plus NDI is equal to capital NI. This implies that G will be equal to NRI plus NDI minus capital NI. For the partial derivatives, we have to take them with respect to both multiplication factors NR and ND for all sources. From here, we can simplify the equation a bit before we take the partial derivatives. Because we know that the number 1 and ni are constant values, this means that their partial derivatives are 0. So we're left with this. Next, what we'll do is separate the partial derivatives for crit rate and crit damage multiplication factors from the jth source. Let's focus on the second term in these equations first. We can distribute the partial derivatives to each multiplication factor. Now, we assume that sources are independent, meaning that an upgrade in one source doesn't affect another. Recall that derivatives describe the relationship of how the change in one variable affects the change in another. So, when there's no change in the output, that derivative is 0. Because of this, out of all the terms in this summation, the only ones that would remain are the case where the ith source is equal to the jth one. All other partial derivatives from other sources are just 0. Now for the first terms. In the crit rate partial derivative, we'll substitute for CR and factor out CD because we know that by definition of the partial derivative, crit damage is treated as constant. For the crit damage partial derivative, we'll substitute for CD and factor out CR since it's treated as a constant. Once again, because the different sources are independent, this means that the only non-zero term from the summation is the case where the ith source is equal to the jth source. All other terms would be 0. What we can recognize is that both equations are equal to lambda j, so we can equate them to each other. And there you have it, a mathematical proof that 2:1 is the optimal crit damage to crit rate ratio, or alternatively, you could have a crit rate to crit damage ratio of 1:2. A major misconception is that the reason why the optimal ratio is 2:1 is because crit damage minor of fixed values are twice of crit rate. This is only partially true, as you need an additional condition, which is that your crit rate and crit damage stats have limited upgrades.
Can you explain the reason for the 1:2 optimal ratio for crit? It boils down to the fact that crit damage is offered at twice the rate of crit rate. What that means is that the amount of damage you're gaining from crit is proportional to the multiplication of crit rate and crit damage, right? The number you're trying to maximize is the result of multiplying your crit rate by your crit damage. The larger that number is, the more damage you do. Area optimization problems are very straightforward. When it comes to something with only 2 dimensions, the largest area is always going to be a square. You want to maximize this rectangle, actually, right? But the way to maximize it is to make it a square, is to make it so that you invest into crit rate as much as you do into crit damage. And the reason why the optimal crit ratio is 1:2 is because when you invest 1 point of crit rate, it's equivalent to 2 points of crit damage.
Okay, don't misunderstand me. Zajef is not wrong. He is definitely correct in what he's saying. However, Zajef is missing important context that makes the problem solvable. To understand what I mean, I'm just going to show 2 different optimization problems. They look very similar to each other. They both involve maximizing area. In this case, it would be average crit, but they are very different based on the condition you impose on that area. I would always mistaken these optimization problems of crit rate and crit damage to be the one on the right, which is that, for example, X could be crit damage is equal to 2 times crit rate. And that does not lead to a finite maximum. that means that there was no optimal solution other than, well, your crit rate and crit damage being equal to 0, which is obviously a minimum, not a maximum. For the longest time, I thought that the 2-to-1 ratio was simply a result of brute forcing calculations and not something that could actually be proven. It was only until I came across this HoYoLAB post that I was truly convinced that the ratio was optimal. And that's why I'm just trying to point out that saying that it's purely because crit damage is twice that of crit rate does not automatically mean that the optimal crit rate to crit damage ratio is 2:1. Like, here's the thing. You bring up an area optimization problem, and the correct condition is the 2x plus y is equal to the perimeter. However, in the context of Genshin, what the heck does the perimeter even represent? In the proof that I have presented, it's important to keep in mind that the average crit was optimized by specifically figuring out what the inputs to that average crit should be. And well, the inputs are obviously crit rate and crit damage, right? Wrong. The inputs were actually the upgrades, NRI and NDI. When you put it in that perspective, it is easy to see that the perimeter is really just NI, the maximum upgrade percentage. In conclusion, I gave an introduction to differential calculus by covering differentials, limits, derivatives, and optimization. With this, I mathematically proved that maintaining a 2-to-1 crit damage to crit rate ratio results in the optimal crit rate by using the method of Lagrange multipliers. An important note, while a 2-to-1 ratio is optimal for your average crit, I'm unaware if this holds when you try to optimize your overall damage output. The reason is because I only focused on crit rate and crit damage, and, well, disregarded other important stats like energy recharge, or, you know, the main stat the character scales off of. Yeah. Accounting for more factors starts becoming a lot more complicated as this adds additional equations into the mix among more conditions to consider and more variables. Yeah, it becomes a mess. There's also the case where crit rate reaches 100%. Obviously, if your crit rate is that high, you might as well just focus on crit damage from then out. But that's pretty self-explanatory. Before I end things off, I think it's important for me to mention that the way I taught calculus here is not the standard way to teach it. In fact, a standard calculus course typically starts with limits, then derivatives, and somewhere along the way you'll probably get a small bit of differentials, but they usually aren't elaborated upon. Personally, I feel that having a great understanding of differentials really goes a long way, especially when we cover the next major calculus topic, integrals. This is why I wanted to start with the building grounds for differentials rather than limits. In addition, I've also avoided commonly taught concepts and phrases such as the idea that derivatives are the slope of a line tangent to the function and that dx is an infinitesimal change in x. While I think the slope visualization is pretty decent, I think it starts to get really awkward once you go into higher dimensions, and well, dx being an infinitesimal change, that phrase becomes really awkward once you get into more advanced math. Fun fact, the differential wasn't well defined until you got into differential geometry, which categorizes them as differential forms. In any case, I want to thank Quantum Thunder for once again helping me better understand the topic regarding differentials and clarifying various things about the topic to me. I'm pretty sure he'll probably correct me if I made a mistake. Or I don't know, maybe he'll put in his own clarifications because he knows more about pure math than I do. I can't cover everything that calculus has to offer, so there are a few areas I can recommend if you want to continue studying. This first one is an absolute classic, 3 Blue 1 Brown's Essence of Calculus. It goes over all of the important conceptual ideas that calculus has to offer, and it does it in a very visual way, so if that sounds interesting, you need to watch it if you haven't seen it already. The next channel, or rather channels, I can recommend are specifically Black Pen, Red Pen, and well, Black Pen, Red Pen Calculus Basics. This guy, well, he solves a lot of problems, so if you actually want to see more examples of problem solving for calculus, I highly recommend his videos. For this third recommendation, this video is more of if you want an understanding on how you would develop calculus for yourself, and it is the video by Suji Lakmo, The Developmental Method Applied to Calculus. Personally, this is probably one of the most satisfying videos I have ever watched regarding calculus, and it actually covers the definition of a limit and rigorously goes over how that definition comes about. The last recommendation I will provide is actually a set of online notes, specifically by someone named Paul Dawkins. It covers basically everything in calculus, so I highly recommend that you check it out, especially if you want some problem solving and even more details about various clarifications and whatnot. So yeah, remember to like the video, comment, and share it with others so they can learn about calculus. There's also super thanks, where you can leave special highlighted comments along with a small donation. It should be found in the bottom right corner of the video, or it's sometimes found inside the little ellipsis. I would love to thank Eternal Donglework for your continued support as a 5-star channel member, as I'm very grateful that you're willing to be so kind and generous. Channel members are able to get amazing perks, like getting to see videos in early access where there are no mid-roll ads, or even members-only videos and posts. Fun fact, while I was still working on the general relativity video, I actually released a thumbnail preview, so Eternal Donglework actually got to know about this topic months in advance. As I've mentioned before, I use calculus a lot in my videos, so I hope this will help you better understand derivations and calculations. Thanks for watching and hope you've enjoyed.